Okay, so let's talk about a couple things. I put up the extra credit opportunity. I don't remember what I said, but was it good?
Yeah, you said three events. If you get an
Oh,
extra
like
credit.
yeah, they're like redeemable coupons, right?
Yeah, there's like three 100% quizzes. If you go to three of them, or 5% for each
Well, I
token.
also I also put this up earlier today. This is with the Grace stuff. So you can get a $15 gift card if you get randomly chosen from this. But Grace is trying to make their meeting schedule and what the activities they do possibly more compatible, so more people can get involved. So there is this kind of a survey thing to take. It puts you into an entry for gas stuff. I really do encourage all computer science students, not just female computer science students, to get involved with this. ACM stuff is a big deal, and we have an opportunity to turn this into kind of what we want it to be. So that's kind of the purpose of this survey, for you to kind of say what are the things you're really looking for out of some sort of computer science club, if you will. But I strongly encourage you to uh, take that student group seriously and try to attend. So if you can fill that out and kind of put in information about when you'd be able to attend and that kind of stuff, I think that would be helpful, so that they can try to schedule things that are most compatible. Let's see. Then for the extra credit dealy flippy thingamajiggy, I put up the whole schedule thing there. So three extra credit opportunities. Each opportunity involves you attending a session and writing a one-page summary. So you have to write one-page summary per thing. You don't write one page for each of them. So you got to write 3 pages if you want three extra credit things. Of a session and what you learned that may benefit you in computer science. Completing each opportunity will award you one extra credit token. Tokens can be redeemed for a free 100% on a quiz, or a homework assignment, or a 5% bonus on an exam. All right, so you can go to the keynote. That's a one-time slot type thing, and then there's 2 afternoon things. That's the same sessions repeated. So pick 2 sessions that you think look legit and go to 2 of them and get a total of 3 tokens, and then you can decide when you want to redeem those tokens. Make sense? All right, questions about the extra credit? Okay, so let's talk about the midterm. Now that extra credit stuff is this coming Wednesday, right? So there's like a whole list of schedules. I pasted it on there, so you see all the stuff that's going on Wednesday. Um, so I encourage you to take advantage of the things that are happening on campus, not just the 3 extra credit things, but go to chapel that day. There's like a lunch and learny type thing going. There's stuff. Take advantage of those things. All right, midterm is going to be on Friday. So what's the date on Friday? 27th. All right, Friday the 27th, because we do not have class on Wednesday because of the Reformation Day stuff, flippy dealy thingy. So the exam will be 10 questions. A majority of them will be programming, but expect 2 or 3 of them to be, short answer essay type questions. I'm going to go through, we'll kind of flip through the book, and I'll tell you which things I think are kind of most important, and you can maybe focus in on those things as you study. Um, the Remember, I have the policy in all my classes: if you bomb the midterm, you come back and do better on the final, I'll replace your midterm exam with that grade you got in the final, but not the other way around. Okay, so you'll have the hour, the 50 minutes, whatever, to take the exam. It'll be designed to take probably 30 minutes for somebody who is like on top of things. So it shouldn't be a time crunch situation if you've been keeping up with the class and all that jazz. Okay, so let's go back here to the beginning. All right. Yeah, I would. I'll ask probably 3 or 4 questions about the table of contents, so you'll want to memorize that. um, yeah, they put a lot of crap in the front of this. All right. So this whole idea of inductive sets of data, I'm not going to ask you questions that get into like the vocabulary of that. What I care more about in the bigger scheme of things is this idea of grammar and productions. All right, so remember you had a homework assignment kind of early on where you had to like define a language like 3 different ways, and we've kind of gotten into this whole grammar production version of it. So I'm not going to have things on the exam that look like this. Um, it's not something that we've kind of danced through this thing, and now we've kind of settled on something that we're interested in. So it would be a fair question for me to say, write a grammar for a language that follows some rules, something like that. Or I could give you a grammar, and you would tell me which, give me some examples of things that adhere to this language, something like that. So you should be able to read grammars. You should be able to write grammars using only the form that we've been using in class. You don't have to go back and learn those other ones. Okay. If you go back and you review from, was it chapter 1 or chapter 2 when we did the zillions of questions? It was chapter 1 questions, right? Yeah, so you had a whole bunch of like introduction scheme type questions, and now we're starting to find that a lot of those actually have something to do with language stuff. Expect to have several programming questions on the exam that are along those difficulty type lines. So probably more in the 1-star category. Maybe there'd be 1 2-star question on there or something like that, relatively speaking. But, I'm going to want to know where competencies are in scheme. Let's call it loosely connected to language theory stuff. I'm going to want to know where your competencies are in terms of reading and writing grammars. And then probably, 4 questions or so are probably going to be focused more on the stuff that we've been dealing with lately with the parsers and specific language constructs. The idea of, let's just keep flipping through here, but certainly variable environments. Like as an example, I might ask you to write a function that takes a list as a parameter and returns the length of that list without using the length function. So that would be an example of you kind of showing me you've gathered this whole recursive stuff, and you kind of can whittle down the list and count the number of things that go in there, and that type of problem. All right, kind of falling back on some of these patterns that we were used to seeing. Yeah, actually, this is interesting. So we're back in chapter 1, and we see this whole occurs free thing. We didn't think anything of this, right? It's like, oh, it's just a puzzle, right? Now we're seeing where those things kind of play in later on. The concept of lambda calculus expressions, kind of that that kind of starts that language of lambda calculus, which is really the language of a procedure-based programming language. So be able to read and write grammars related to that. Yeah, so here's like all those functions starting with, duple and invert, things like that. Plan on having to write, 2 or 3 or 4 questions like that, those kinds of questions. So you might go back through and redo these without looking at your notes, just practice them. And the hope would be they would be substantially easier this time around because you've had lots of practice doing this stuff. I will probably have a question on there dealing with map, but only one question. Remind me, what does map do? Okay. Anything special about that function? Yeah. The function that it maps a function onto each element of a list. So it takes a function and it takes a list and it applies that function to each single element of that list. What kind of animal does map ultimately produce? What's the output of map? Cat, dog, symbol, list. It's a list. Okay, so it takes a list, applies the same function to each element of the list, producing a new list with the result of that function being performed on each element. All right? But that function that you're applying to it takes in one parameter, an element, a list element. That one parameter could be a list. It could be a list of lists. It could be all sorts of things, but it only takes in one parameter. Okay.
That question most likely be like rewriting a function to then use map instead of the existing implementation. Or could be anything.
That's a good question. It would probably be a question, I'm just kind of thinking how I would portray it. Something like, I would pick a problem similar to the problems we did in this chapter 1, like all these like little drill ones. I said, solve this problem, you must use the map function, something like that. So probably something that is actually made easier using map, but rather than me I would probably tell you to use the map function for this, almost like hint, hint, not even saying the map function might be helpful, but saying you must solve it using the map function, probably because it would make it shorter. So chances are whatever question that is, it's probably going to be a pretty, assuming you understand map, should be a pretty easy question. Does that make sense? Okay. It would be fair, kind of going back to the whole grammar, writing grammars, reading grammars, give me examples of things that match a grammar. It would also be fair for me to say, which of the following do not match the grammar or something like that. So you should be able to handle all sides of that problem. Be able to write examples of things that match a grammar, view things that I'm claiming might match the grammar and telling me whether they do or they don't. All right. Okay, so then we're starting to get into the variable environment thing. So certainly talking about the, I might show you the language for this extend env. We have this environment. So I might give you a grammar that looks kind of like this. Let's use this as an example. All right, so an environment is either the empty environment or it's an extend env. What kind of animal would this be called? Is that a constructor? We're constructing an environment using the extend env constructor. And extend env takes a variable name, the value associated with it, and then the environment that we're extending. That's what that constructor takes three parameters. I might ask a question like, what's the limitation of this variable environment? What's weak about this variable environment? Each environment only has one variable. Okay, why is that a problem?
Because ultimately to solve most problems, we might want one variable.
Okay, so it's pretty common. So when we think about, you could explain it something along the lines of like scopes become more difficult. So as we typically think about variable environments, we're thinking about things in terms of scopes. Like everything that was defined at the top of this function belongs to this function, right? So now if you're having to say, well, here's three variables, so this variable is defined in terms of this variable is defined in terms of this variable, they need to be defined in that certain order. So even within a scope, order still becomes important because that's when they were first born, if you will. But we certainly, it would make sense for us to have less fluff. Almost this goes back to this example of XML versus JSON. They both solve kind of the same problem, but XML is a lot more bloated just because there's a lot of fluff. So if you were to look, if you had a program with 30 some variables in it across 3 or 4 different functions, if you looked at our extend env version of that thing, it would be like a whole bunch of parentheses, just crazy looking stuff, right? With very little substance. You have 30 total variables across 5 million curly or parentheses or something like that floating all over the place. All right, so it has a limitation of being bloated, but that's still, it's representing information. This kind of goes to what we've been talking about more recently with our parsers, where why are we parsing parsing the inputs? Well, we're parsing the inputs because we add some semantic information to it that allows us to execute it more quickly later on when we actually go to run it. So even though this environment ends up being very bloated, if you will, it kind of is easy to process after the fact because you only have one variable value pair. And then if we wanted to, and we're going to start getting into this shortly, but if you wanted to add the construct of a scope to this, what would a scope be? A scope would be a nested list of extend envs housed inside of a scope, right? And then you might have a list of scopes where scopes can live inside of other scopes for when you have to unravel something. You check locally, all variables resolve to their most local definition. So we say, is this variable defined somewhere in here? If yes, resolve it. Otherwise, kick it up to the next possible scope, right? So if you have two functions that are sitting inside of a program, these scopes don't interfere with each other. They don't interact with each other at all. So if I'm in this guy, I bounce up here, not over to this scope. All right, so, sometimes I might ask a question that doesn't really have like a clear-cut correct answer. I might want to see your explanation of why something is strong or weak, or what are the pros and cons of something, showing me that you're kind of thinking through the language construct aspect of it, where there might be many right answers or many reasonable answers, but then there's some answers that'll kind of show me that you don't understand that concept. Does that make sense? So on those kinds of questions, I'm looking more for understanding and competence rather than, the perfect words for explaining the issue. So anything that's along the right lines, or at least shows a level of critical thinking about it. Even if you made an argument that in class I might say, yeah, but is that really a weakness? Because what about this, and this? That doesn't mean it's a completely ridiculous statement. You can make an argument either way, so that would be okay on an exam. I want to see that you can make a argument that's logical related to language theory stuff. Make sense? All right, so variable environment stuff. It would be fair for me to, and this isn't even saying anything different than we've already discussed, but I could give you the grammar that looks like this, and then give you, say, write a function that resolves the most local value of a variable or something like that, which you've already written before, isn't really any different than all those questions in 1.1 whatever, but in this case happens to relate to kind of walking through a list structure that's in a specific format. All right, so you should be able to check to see, does this match the variable name I'm looking for? If yes, give me this value. If no, extract the invariable, the next level, the next environment, and check there, so on and so forth. All right, so then we start getting into these interpreters. This was talking about it before we really started talking about parsers. So when we talk about an interpreter in general, we're taking in our something that matches a grammar, and we're reacting to the things that we see. And what we're doing is we're really asking questions related to, if we look at this, let's go to the lambda calculus example. That'll be easier for us to talk about. So something in here, we might just say that this guy must be a lambda if If it's not an identifier, it must be a list. Why? Because the only other productions involve lists. Well, if the car of that list is the word lambda, that guy must be that production, right? Well, what's the weakness of just making that assumption? That if I see the word lambda in the car of a list, it must be production 2 of an LC expression. We've been doing it, but why is that problematic? That would be another question about kind of competence. Yeah, I mean, it doesn't, it ignores error checking, right? So, we're making this assumption that if anybody throws me a list that has a lambda in it as the car, that's a lambda expression. We're just hoping that what they give us next is the catter is a list containing one identifier, and the CADDR is the body of that lambda calculus expression, but we don't know. They might have just given us a list with lambda in it. Done. Right? So we make some poor assumptions with that in mind. Now, that's another reason for a parser, because a parser allows us to kind of handle the two sides of the problem separately. One side is validation, right? We're going to go through and we're going to validate your input and then turn it into a alternative input that maybe we can rely on a little better. The idea is if we have parsed data, that's already been validated. So at that point, if we see something whose car is a lambda expression, we know that that guy is legit. We've already done all the screaming and yelling that we're going to do about that, and at that point checked it. So then when we write the function for actually interpreting it, we're just focused on the interpreting logic, not the error checking logic at the same time. So that's kind of the process of separating parsing and interpreting from each other. Now, even though we haven't actually been doing the error checking in the parsing process, because we've been wanting to focus on the parsing process, so we're not really talking. We're talking the talk, but not walking. What is it? Is it walking the walk? Talking walking. We're not error checking because we're lazy, is what it comes down to. All right, but there is a rationale to when we might do that. So, for instance, it would be fair for me to ask a question like, if we were going to error check our inputs, what would we do that at the time of parsing or at the time of interpreting, and why? Something like that, another competence type question. I mean, I guess you could probably make an argument that you can do it at the time of interpreting, and you have to be pretty compelling, but I suppose you could make that argument. Maybe for certain languages that, if it's a language that doesn't have a lot of complex constructs, so if it's not lists of things like this, if it's just basically the language of numbers or something, maybe even the idea of parsing doesn't make sense. So some languages might not even, we might not make the assumption that it would be parsed ahead of time. A language needs to be complex enough for us to for it to be worthwhile to parse it, I guess. Okay. So again, be able to look at this grammar, be able to do stuff with this grammar. And one of the things I'm going to be looking for on the exam, again, I keep using the phrase competence, is when I show you something like that, the grammar for lambda calculus expressions, and I show you, let's go way back near the, some simple grammar for, I don't know, binary trees or something like that. Just find what our first grammar that looks reasonable to us is. Or that maybe an S list. Yeah, here, list of integers. Something like that. So if I show you a grammar for lambda calculus expressions, I show you a grammar for list of integers, all of us in here at this point should approach those two things identically. Just because lambda calculus expression sounds more complicated than list of integers, you're just following the identical rules, right? You're dealing with the grammar on a production by production basis, and now that we've introduced this idea of a con, you're probably going to have an element of your con for each of the productions. Does that make sense? So don't flip out the second because I very likely will put a completely made up grammar on there. That does, I mean, it might even just be there to be funny. Yeah, I might have a grammar around the language of Teenage Mutant Ninja Turtles or something like that. All right, so don't read too much into what the name of a grammar is. Read the grammar, look at the productions, respond to the question. The name of it is completely unimportant. That make sense? All right, no data type stuff. I do like binary tree E type stuff, so I would actually be surprised if there won't be some grammar, some problem dealing with binary trees. It probably wouldn't be a horrifically difficult thing. It would probably be me having an effort of having you manipulate something that wasn't just a flat list, a list containing maybe 1 or 2 levels of lists within it, kind of forcing you into the recursive nature of things, as opposed to me trying to give you something that's tricky. You know, like for instance, like if you remember this one, this whole red blue. I think this was this the one we did where we labeled them, where you had to spend about 10 minutes figuring out what they were asking. I think that was, might not have been that one, but there was another one in here where we had to, you know, we had to label something either a red or a blue or something.
We did the other one.
Yeah, whatever it was. Yeah, whatever that one was, where you actually had to sit there for a few minutes and read it till you figured out what they were even asking you to do. Don't expect things. If you are having problems understanding what I'm asking you to do on the exam, come up and ask, because my intention is not to like trick you with the question. Make sense? Okay, so I don't intend to give you questions like that on the exam. Okay. And then we get into the stuff that we've been dealing with more recently. So that's parsers in general. And what does a parser do? I were to ask you the question, what's a parser and why do we need them? What would you say? Just exhilarating. So we just leave that one blank on the exam? What's a parser? What does it do? Okay, yeah. Adds semantic meaning. Marks up, makes our, well, more than likely, grows the code, right? We're adding stuff to it. Sometimes we might be replacing something, so we maybe will luck out. It won't actually be much larger. I guess it could be smaller, but we are potentially error checking. But more importantly, we are putting our code in a format that will make it easy to interpret later. Okay, we're manipulating it so interpretation of it becomes easier. That's the purpose of parsing. Therefore, you might back off and say, well, if I have a language in front of me, do I need to parse it? Well, if you parse this, will it make your life easier when you go to interpret it? If the answer is no, then maybe you shouldn't parse it, right? It's kind of simple enough as is. But if you could say, yeah, you know, life would be easier, or yes, error checking is important, then the whole parsing step effectively is your error checking step, and whether you actually change it or not, right? You might just say these, you know, if you want to make a language fairly cryptic, and actually this is a language that actually exists. So rather than, you know, like we run into something that says like starts with a lambda, we might label that as a lambda-exp, right? That's us marking it up. Why didn't we just call it 2? Because it was production 2. Why did we put a 2 in front of it? Or a 3 in front of it if it was the app expression? Why did we label this lambda expression versus or app expression rather than 2 and 3? Go ahead. Okay, potentially. Who reads the parser? Who uses the output who uses the output of the parser? Yeah, the interpreter. Yeah. So really, your answer has everything to do with the human looking at it, right? Now, if it's not a human looking at it, or it might sometimes be a human looking at it, is there ever an argument that you can make when storing a number, this is production 1 or production 2 or production 3, makes more sense than labeling it something that's clean? Like lambda expression or app expression or var expression? Would it ever be better to label it as a number? I'll give you the hint. The answer is yes. So now the follow-up question is why or when? That's actually something we use every single day with our computers. It's related to memory. Oh, it's a good guess if you say computers. What's a CPU? Collection of magic trick guy, right? Because knows how to do a whole bunch of stuff. All right. What's assembly language? Okay. So it's a low-level language, right? What's a low-level language? What does it mean for a language to be a low-level language? Okay, so one-to-one relationship with the CPU. So every line of code we write in assembly language translates into one of those magic tricks on the CPU. If you were to, so there's a conversion there, right? So we write a line of code. Let's say I say move AX comma BX, something like that. So this is moving into this memory register the contents of this memory register, something like that. This is the assembly language version of this. This is human readable. I'm moving memory from point A to point B. Does the CPU understand this directly? What does the CPU actually understand? What's our default answer when we talk about what's the language that computers understand? Ones and zeros, binary. So we need to somehow turn this guy into ones and zeros, don't we? How would you convert that into ones and zeros? Somewhere, we're kind of going back to the, beginning of kind of computers. How do we take things and allow human beings to write things? I mean, none of us want to write assembly language today, but we can. Right? We can write assembly language. We don't want to, but we can. Now, none of us want to write machine language. Technically, we could, okay? But it's not a friendly thing to do, and it's not something we'd be anywhere near efficient at doing. So the efficiency for us is we'd write it into this format, worst case, and then have it converted into machine language. But somebody had to invent that conversion aspect of it, right? How does that happen? How do we convert? How do I take this and convert it into the equivalent machine language? Is this guy just a function call? It's a function. Might we call that a magic trick? All right, it's a magic trick that happens to take 2 inputs. So this magic trick kind of knows how many inputs it's going to have, right? Now, how many magic tricks does a CPU have? More than a couple? So let's take our modern Pentium ones. Maybe it has, 500, 600 magic tricks. Probably more than that. A lot of magic tricks. We go back to, 8086 or something like that. There was far fewer, but still plenty of magic tricks they could do. Now, we know the move command as move. That's the name of the magic trick. But under the hood, don't you think the magic tricks are probably indexed? This is magic trick 1. This is magic trick 2. This is magic trick 3. This might be magic trick 17. So out in front, and let's say we're dealing with a 16-bit computer. This magic trick, or a 16-bit CPU, this magic trick would be represented as a 16-bit value. So if it's magic trick number, let's use 1, because it'll be quick and easy, then I would have 15 zeros followed by a 1. That's the magic trick number. Next, I would have AX and BX, or our 16-bit registers. So I would have the memory, they have a name. Okay, these are AX and BX are kind of like primitive types for our CPUs. Okay, they have a hardwired location. All right, that's going to be some 16-bit value for that location of that guy. So you'll have another 16 bits of zeros and ones. That is the hard-coded literal location of AX, that memory location. And same thing for BX. So in this particular case, you would have 48 bits, 48 zeros and ones representing move AX, BX. Does that make sense? Now, would you say that taking our input like this and converting it into something that looks like this is an act of parsing? Or is that at least parsing like? We're converting it into a format that will make it easier for us to execute the code later on, whether you want to call it interpretation, whatever. We're going to ultimately run this code on the CPU. And it would probably be in our best interest for our CPU to not have to do some stupid mapping of move when it could be actually crunching numbers, right? So we want it to be able to directly go to its instruction set, which is going to be loaded in memory, probably the first portion of memory. So you can just zip to instruction set 1, in this case. Don't have to go very far. And you're right there at that instruction, and then you just execute it. That's where the magic trick lives, on the CPU. That make sense? All right, so this idea of parsing has been around for a long time. This isn't something we just invented to make our lives more complicated. But only parse if it's going to benefit you having it in a different format. Okay, so certainly be able to have conversations about parsing versus interpreting. Now, we haven't actually started writing. I say we haven't actually started writing. We have written interpreters, but we haven't written interpreters while we knew we were writing interpreters. Okay, so the next step, obviously, for us is to start interpreting the languages that we're parsing. All right, so the exam itself is not going to ask you questions specifically about interpreting, other than the purpose of parsing is to prepare your input for interpretation or for execution. You can use those two terms interchangeably as far as I'm concerned. From a language construct perspective, it ultimately comes down as to what type of language it is, whether or not you're going to call it interpreting or you're going to call it executing. Same thing. Okay. In fact, our book typically just calls those functions apply. Okay. Apply these inputs to this code, go. And what's the output, however we got there. Okay, so let's see. Anything else? We have started looking at this language of expressions, which is just a more complicated grammar, right? So we're looking at a kind of had 2 different levels. Not so important for us right now, but we really have a language of expressions. And what we've decided is that we would just have at the very top level, we would just put our nested expression stuff into a little baggie that we call a program. That makes sense? So really that program aspect of this guy right now is pretty unimportant. You know, it's almost there as a placeholder for where we're probably going to end up going with this. Especially since programs likely come with an empty environment, if we kind of roll forward a little bit. Okay. I will probably have a question on the exam that will force you to use a let at some level. I won't. It would be fair game for me to ask the question, what's the difference between a let and a let star? I don't know if I will ask that. I feel like I would have to be like running out of questions to ask, or needed to ask a question that wasn't going to take too much time because some of the other ones might be too time consuming. But just real quick, what's the difference between a let and a let star?
Star, you can define a variable in terms of its
Okay, so let star allows us to define other variables in terms of variables that have previously been defined inside of that let star. So in a let star, I can say A equals 5, B equals A. Does that make sense? Because A had previously been defined inside of that let star. I can define another variable like B in terms of what A is. Powerful, if that's something we wanted to do. So I might ask you a question that involves you understanding that. Programmatically, though, if I probably will try to ask a question that will involve a let or force you to use a let. Similar to what I said about map, I might say solve this question using a let, but it would always be solvable using a normal let. I won't ask a question that would like require you to. You should understand the difference between a let and a let star right now, but it doesn't really help us to prove a point of me giving you some kind of question that's tricky enough where having a let and a let star might make a difference. Now, do you ever actually need to use a let star? What's the alternative to using a let star? Yeah, do a let inside of a let. Right, if you need a variable B defined in terms of the A, you do a let that you define the A, then in the body of that let, you have a new let that defines B in terms of the A, because now that guy's available to you. In fact, realistically, under the hood, I think let stars are probably implemented in terms of nested lets. You wouldn't be surprised at the very least, right? Okay. So certainly lets would be something I would expect you to be comfortable with on the exam. We haven't really talked about types yet. We had a short discussion about types, but I would say I won't ask you questions about types. Really what we were talking about is kind of looking ahead about this language, like what's this ultimately going to evolve into for us? Because we're in kind of a precarious situation right now where we're all programmers, right? We have this pretty deep knowledge now of high-level languages like Java and things like that. So we kind of know what a professional programming language designer ultimately would produce. We can look at examples of C# and Java and Swift, whatever. Those are examples of good, well put together, probably complex languages that we don't want to have to do for our homework, right? If your homework assignment was write Java, probably would suck. It would be a whole lot of stuff very similar to this, but a lot bigger than this grammar, right? Somewhere in there, there's a grammar that could represent the Java programming language, but probably a relatively scary looking grammar, at least from a list of production perspective, the different things that the Java language accepts. But we can kind of look ahead here and say, oh, well, whenever we have an if in Java, this expression is always what kind of expression? It's a Boolean expression. Now, something that's kind of interesting for us is, wasn't this idea of a Boolean expression something we learned very, very early on in our learning how to program world? We like, Boolean expression, any expression that boils down to a single value of true or false. That was something that was like day 3, right? One of the very first things that we learned when we were talking about programming. Yet we've spent half a semester learning how to put a programming language together, and we still haven't gotten to the point where we're able to label an expression as being of a certain type. Does that make sense? Something we think of as being so trivial is pretty far down the line. Having a language where types mean anything is something we're going to be coming into right now. As an aside to that, we've talked about loosely typed versus strongly typed languages, right? What's the difference between a loosely typed and a strongly typed language? One looks like Scheme, one looks like Java. What's a loosely typed language? Which is Scheme a loosely typed or a strongly typed? Loosely typed. How do you know? You're not. Well, you do define them, but you just don't say what kind of. You don't say what they are. you knew what you were talking about. Where a language like Java or any C-based language, right? Those are all strongly typed, where we say this guy's built to hold an int, or this guy's built to hold a char, so on and so forth. Do types exist in all languages? When I say that a language is loosely typed, that doesn't mean that types don't exist. It just means that types aren't explicitly mentioned. They still have to exist. That's why we have that whole type inference engine, right? We have to figure out what kind of value is this before I can do stuff to it. Now, since we are seemingly at this point writing languages that are loosely typed using a loosely typed language, which isn't a requirement, but that seems to be the direction we're currently rolling, right? Aren't we going to need to implement our own type inference engine? Something that we pass something to, certainly from an error checking perspective. We pass something to, it says, is this a guy that's the type that I'm allowed to, is this guy a Boolean expression? Is he boiled down to a value of true or false? Because that's what I ultimately expect here. Right now, my language, my grammar hasn't defined what a Boolean expression is. But this guy probably should be one of those. All right. Questions about the exam. What to expect, blah, blah, blah. So everybody's going to get high A's? Or at least going to go do the extra credit opportunities on Wednesday? something in there? Okay, the answer is yes. Conversion questions are always a threat on my exams. It will depend on, because with this, I need to be pretty careful about time. So I'll probably write the questions I definitely want to ask first. And if I need a filler, something that's like a 2-minute question, I will. So it's certainly possible. But I'm going to pay pretty close attention to an exam that the average student in here should be able to finish in about 30, 35 minutes. I don't want it to be a time pressure thing. Some of you, it will be a time pressure. That just lets you know you're not quite where you need to be, and then you just fix it on the final. But this is a harder exam to write because I got to figure out how long it's going to take you to do some of the things. All right? But always a threat. All right, I will see everybody hopefully I see many of you at one of the sessions on Wednesday. And remember, there's not like sign-ins or anything. You'll email me your one-page papers and you'll tell me what thing you went to, and then I'll end up creating a column in the grade book for tokens or something. That way it doesn't impact your grade, and then we'll figure it out. All right, I'll see you on Friday.